Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is Jamon Bowen. Jamon is Director of Sales Engineering at Texas Memory Systems. Welcome, Jamon.
Thank you, Rich. Very happy to be here.
Thanks for coming on the show today. I understand that you guys have some slides to go through for us. Do you want to just start up with that?
All right, great. So first I'd like to give you just a little bit of a background on Texas Memory Systems. We've been in the industry for more than 32 years now, making solid-state disk systems. Before, I would say they became very popular and more of the household name in the IT community. We're a private company, and we're global in presence, and have been continually making new products and have a very broad SSD portfolio. A lot of people are interested in what TMS does over this whole time frame because we make solid-state disks. But what I think is the easiest way to understand it is if you look at the typical Ramsey application matrix, what you'll see is that we serve a large number of industries: the financial, government, e-commerce, HPC, and telecommunication. And there's a lot of different applications that we cover, but at the end of the day, our products are really a performance solution to various problems. So we end up doing lots of database acceleration in the commercial market and a lot of unstructured data and batch run type jobs acceleration in the HPC space. Now, if you look at the Ramsey product portfolio, we really have three different types of solutions with a number of offerings under each one. There's RAM-based network-attached systems, and these are RAM-based SSDs that have some backup batteries and a persistence mechanism to make them non-volatile. Now, these were what SSDs were for almost 30 years. And now they're a much smaller part of the market used primarily for persistent logging applications. Although there have been some use cases in the past using them for metadata on a large parallel file system. The other two types of products are both flash-based, and that has really been an area of growth, not just for Texas Memory Systems, but for the industry as a whole. And we have two basic types of systems that are deployed. There's a flash-based network-attached system, and then there's a PCIe SSD. And in this overview, we're going to talk about some exciting news on both fronts on this flash system space for TMS. So I'd like to go into the details on a new product that we're announcing in the Ramsey N70 PCIe SSD. This is our next generation PCIe SSD solution and takes advantage of a lot of the things that we learned with our Ramsey N20 SSD and takes advantage of a lot of new technologies. This is using what we're calling our Series 7 flash controller that leverages high-speed Toshiba SLC flash chips to make a very powerful product. And we'll be using this controller in a whole host of different systems going forward, as it's really the core building block of what makes our flash SSDs so fast. This is a half-length, full-height PCIe product, and in its full configuration, it has 1.28 terabytes of raw capacity. Now, we RAID the flash chips, and there's quite a bit of over-provisioning that's used to make sure that we're fast for both writes and reads. And so at the end of the day, you have around 900 gigabytes of usable capacity. And this takes advantage of a lot of the things that we did on our previous PCIe product, where we make sure that it's a complete solution and all of the flash management, heavy lifting that has to be done, is done on the card itself. And what that means is there's an embedded power PC, more than 4 gigabytes of RAM used to handle all of the flash lookup tables, and then many flash controllers that are each controlling a limited number of chips. And that lets us have a very lightweight driver on the host. On the Ramsey N20, for instance, we had an open source driver that people could use, and it allows us to have a very high sustained performance. And when you compare this to the Ramsey N20, we have 3 to 4 times the performance because we really focused on making sure that we could have a very high bandwidth solution. And I'll talk about why we did that in some of the use cases configurations. For some of the background, it's a PCIe by 8 Gen 2 connector for that approximately 1 terabyte of flash. It's twice the capacity of our previous PCIe product. It's half the size in terms of physical board space, and it has a longer lifespan since it's still leveraging the SLC flash and some advanced technology that we've implemented. So a very exciting product announcement from Texas Memory Systems. What we're also just bringing out covers our full multiple product offerings into the SSD space, and we're announcing Storage Performance Council benchmark results for the Ramsey 630, and that's our flagship SAN-attached external SSD system. And I have some highlights of the results. We're releasing both the SPC1 and the SPC2 benchmark results. Now, on the SPC1 front, that's the high IOPS workload for the Storage Performance Council that has quite a bit of difficulties for flash-based SSDs. It requires pre-filling the device, proving sustainability, and it's a heavy random write test. And we're very proud that we're going to take the top SPC1 audited performance number at over 400,000 SPC1 IOPS. And that is going to reset the bar higher for the SPC1 results that are submitted. And what's interesting when you look at that number is we end up having the top SPC1 IOPS. We do it at extremely low cost per IO per second, but we're also competitive in terms of cost per gigabyte with the disk systems that we are displacing. In conjunction with this, what I think will be particularly interesting to the HPC audience is that the Ramsey N630 is going through the SPC2 benchmark as well. SPC2 is a bandwidth-intensive test. It simulates video on demand and additional workloads to prove the mettle of a storage system for these high bandwidth type of use cases. And what we've done is for the SPC2 configuration, we use the Ramsey N630 with 10 QDR InfiniBand ports and are able to really demonstrate what an SSD system that's designed for high bandwidth can do. We'll have the number 3 SPC2 results at just under 8 gigabytes a second. And again, this is a sustained audited number that you can read all of the details, including pricing and full disclosure, at the storageperformance.org website. So those are the big announcements from Texas Memory Systems. I'd like to touch base on why these matter to your audience and to give you a little bit more background on how people use it. So if we look at the HPC Ramsey architecture, there's really 3 different ways people are using our products that enable some really exciting ways to leverage solid-state disks in the HPC space. The first one is what I consider a single application scaled up storage. And this is using a parallel SAN file system to attach a fairly limited number of servers to SSDs at the core, in this case, the Ramsey systems. And what this enables is applications that have the ability to be parallelized but don't have the capability of having the data segregated per process. So not necessarily the traditional HPC cluster workload, but a lot closer to what you would end up getting a NUMA architecture or do a high level of message passing within an HPC cluster setup to try and tackle applications that require this total access to the data set. And what you're able to do with the SAN shared file system is have tens, 20s, hundreds of terabytes of solid-state disk capacity with hundreds of gigabytes of interconnect so that every node has full access to the entire data at the low latency that SSDs are capable of. And that really unlocks the potential of these applications which don't have a great solution otherwise because they require that type of random access to a huge data set. The second type of architecture that is growing in popularity is what is a scaled out, effectively shared nothing type of design. And this is the PCIe products place. What PCIe SSDs are, in effect, is it's direct attached storage on steroids. And by putting one of these cards in a server, you have an unbelievable amount of local performance within that one ecosystem of that one server. Like on our Ramsey N70, you can do over 2 gigabytes a second of bandwidth locally. And what's become more and more common is there's cluster applications where the data is distributed within the servers using some sort of Hadoop cluster or other architectures. And the PCIe SSD gives the capability to just have a lot of performance and a lot of capacity right within the compute node. And that type of architecture is definitely becoming more and more exciting and a key spot for PCIe SSD adoption. The last architecture I'm going to touch on, I would say, is the most common of the HPC architectures for storage systems today. That's the parallel file system where there's a large number of compute nodes connecting in through a network to a number of either object storage server nodes or network storage domains that are sending out the data. And from there, where we're finding people use the SSDs, the RAM SANs, quite effectively, is behind the network storage server tier as metadata and more as primary data. And what that allows is it's similar to that SAN shared file system, but it works for these very high performance clusters. And what we've shown with the SPC2 details is that you can build an exceptionally capable high bandwidth setup with a fairly limited number of RAM SAN devices. And so these are all really exciting advances in what you're capable of doing with solid-state disks within the HPC environment. So this is Jamon Bowen from Texas Memory Systems, and I have some more information on this that I'm posting from time to time on my blog, and you can look at it at storagetuning.wordpress.com. And hopefully I was able to cover a lot of the new announcements from Texas Memory Systems, as well as where people are using this as in a practical way in the HPC space.
You guys have been doing this a while with the RAM products, correct? You've been in this space for how long?
For just over 32 years.
And, you know, it seems like there's just a wealth of upstarts in this SSD space. Do you find yourself in a defending market share kind of position?
So from our point of view, we really take advantage of our hardware engineering expertise and have really taken advantage of the developments at the component level to bring bigger and faster systems to market. So you mentioned that we've been in the business for 30 plus years doing RAM-based systems, but today more than 70% of our systems are flash. And it's that deep hardware engineering that allows us to be able to adopt the new technologies and take them to a different level. And what we've found is that by having a deep hardware engineering team that does the actual FPGA development, that we're able to be continually about 1 to 2 years ahead of the competition in enabling flash architectures that may not have the mass deployment characteristics yet, because we have that quick turn design cycle and we're able to use more chips than some people would think is practical at the time.
So in the HPC space, are you continually getting people that are asking you to kind of push the envelope? You know, they've got these specs like we want 50 gigabytes a second. Do you get those kinds of RFPs in front of you?
Absolutely. That's where it's new for SSDs to be able to handle these high bandwidth use cases on a at a level that disks can, because disks are fairly good at sequential bandwidth. And so it's great for us when we're coming into these environments and they're looking at doing 50 or 100 gigabytes a second, because we can do that in just part of a small rack with a low power setup. And outside of the HPC community, there's not a lot of other customers that have those requirements yet.
You think that's something that might be coming around the pipe for enterprise and cloud kind of operations?
I'm sure it is. The network becomes faster at a faster rate than processors increase their speed. And that leads kind of enterprises to adopt architectures that look more like HPC type of setups. And what I've found is that in the enterprise, when they're doing a cloud type of deployment, one of the real things that solves is the problem that people aren't very good at writing parallel code. There just isn't this level of software engineering expertise outside of the HPC community that's able to write something that's going to use hundreds of thousands of threads on multiple processors. So in the enterprise, they've kind of done something to make it easier on developers. They have this cloud architecture doing virtualization of the server tiers, and then they just run 10,000 server images and in effect end up with this parallel architecture by this back-end management structure. I see a lot of what the enterprise is doing today as mirroring what HPC has really led the envelope on, just with a little bit simpler type of hierarchy so that multiple people can work on it simultaneously easily.
So I saw in some of your other slide decks you had some patents to talk about. Are those around the memory controllers, or what are those about?
So there are several patents that have been coming out from Texas Memory Systems, because obviously the SSD space is becoming very crowded, and we're taking advantage of the fact that since we're solving problems earlier in the SSD community, since we are pushing the envelope with our designs, is we're making sure that rather than just solving the problems, that we take the extra steps to file patents and explain how we've done it so that people can take advantage of the R&D that we're doing. And some of the patents that we just came out with quite recently have to do with error correction that you have to deal with within Flash. So I think there's a pretty good understanding within the community that you have to handle writes in a special way with Flash. But I think what is missing in a lot of cases is an understanding that that's just the tip of the iceberg. You also have to deal with read problems. You have to end up doing many, many, many bits of error correction within a small block, and you have to handle plane failures. There's all of these idiosyncrasies of Flash that make it a very difficult media to work with that end up driving cutting-edge type of developments in the error correction and handling the media. So one of the patents that we just brought out handles read disturbs. What read disturbs are is if you read frequently one part of a Flash block, you corrupt the data that's next to it. And that's a problem because you're not reading that data, so you have no idea that it's become corrupted. Now, there's quite a bit of bit correction that you have to do with Flash anyways, but if you don't bother to account for this problem, then you'll end up with data corruption and data loss. And so what we implemented is, in effect, a read leveling technology that makes sure that we stay under the thresholds where the heavy read part of the chip is going to be corrupting everything else. And then when we get close to that level, we make sure that we move the data to a new location and let it start fresh.
So as you guys look out to the future with the roadmaps of these Flash memory devices, the density, of course, keeps going up. Are those problems you just talked about, are those going to multiply, or are they tackling that problem as well?
They are mainly multiplying. The main problem that Flash manufacturers at the chip level are trying to do is drive the cost per bit down. And they're trying to address the consumer market of SD cards and really consumer type of use cases that are not really all that performance requirements. It's more of a power savings and space and cost. So certain things that are fine in the consumer space, like 1,000 write array cycles for a camera card, is probably fine if it has all sorts of capacity. Just don't work in the enterprise. So what we've found is kind of two things. Number one is several years ago, or I guess a couple years ago, everyone was predicting that MLC would take over because of its cost advantage and its ability to store more data in the same chip at the cost of having it be less reliable and wear out more quickly. And what we've seen is that the SLC has been kind of brought back to the front because each time they shrink the chip, the costs go down, but the error rate goes up. And so what we've seen is that it's become more important to have the enterprise-grade characteristics each time that you shrink it, and more you have to deal with the flaws of flash rather than just the benefits of the low power and being able to surface mount your storage within your application.
So, Jamon, I want to thank you for coming on the show today. I guess I got one wrap-up question. You're deep in this technology. There's a lot of players coming in and all kinds of venture money. What keeps you up at night?
So what keeps me up at night is that as more players come onto the market, there's different quality offerings that have different price points and people have different levels of experience. The biggest thing that I worry about is that people will try what's really a consumer level flash product, have a bad experience, and then write off SSDs entirely. And what I really think is important for people to understand is that there are serious differences in the hardcore technology side of it, and to look at the published benchmarks and see the back-end R&D and understand that not all SSDs are created equal.
Well, great. Hey, Jamon, I really enjoyed today's talk. I think you guys have some very exciting things going on. So thank you for coming on the show today. And I was just thinking, maybe we could check back with you next time you got a product generation come around the pike and just check in and see what's going on. Does that sound good?
That sounds great. Thanks for having me.
You bet. You bet. Okay, folks, that's it for the Rich Report today. Stay tuned for more news and information on high-performance computing.